Heat and reactions. So first thing we need to talk about with heat and reactions is, well, what is heat? Because what you think heat is and what heat really is are probably not the same thing. We have to start with something known as kinetic molecular theory, which is simply stating that molecules and atoms are always in constant random motion. It's one of those things that people are like, I'm not so sure about that. Well, you can prove it pretty easily. So for example, if you turn off the air conditioning in your classroom and you light a match on one side of the room, probably within 10 seconds you can smell it on the other side of the room. Well, if there were no air current, if there was no moving air through the room, how did the smell go from one side of the room to the other? Well, it's because the air molecules are moving in the room and they carried it with them. Same thing, if you take a drop of food coloring without stirring it, drop it into a glass of water, it will diffuse over time. Why? Because the water molecules are moving and they move it around as they move around the glass. And so those molecules are always in motion. And so that is just one of the things that is a bedrock of how we think about how things behave in terms of heat, and especially when we get to gases. So temperature then is defined as the average kinetic energy. So something that is hotter or moving faster. Okay, so that's what we call temperature. So the diffusion idea, so like the drops of food coloring, if we had like almost ice cold water, it would diffuse slower than if we had really hot water. Because the hot water, the molecules would be moving faster, and therefore it would spread the food coloring around the glass faster. And this can be, you can do this in an experiment and you can show that this is true. And so you can see that this is what's going on. Then what we say is heat then is the transfer of this energy, this kinetic energy, from hot to cold, or high kinetic energy to low kinetic energy. For this reason, we would say that cold is the absence or the absorption of heat. You cannot create cold. It is like you can't create darkness. The only way to create darkness is to remove light, because darkness is the absence of light. In the same way, cold is the absence of heat. So a refrigerator doesn't create cold. What a refrigerator does is it pulls the heat out of the refrigerator and puts it into your kitchen. You know, that's why growing up, we would always, like if we had wet shoes, we'd always put them at the bottom of the refrigerator, because that's where all the hot air would come out and it would dry our shoes, because that's all the heat that was in the refrigerator, and it gets dumped into the kitchen. Same thing with an outdoor, with your air conditioning unit. You know, you have the big fan outside, the part of your air conditioning unit that's outside. And if you put your hand over it while it's running, it's really hot. There's hot air coming out of there. That's all the heat that used to be in your house. So it's not so much the air conditioning is making cold. What it is doing, it is removing heat. And so it's just one of those things to understand about heat. All right, so when we come into heat and reactions, what we want to say is there are two types of reactions. The heat can be given off, or the heat can be absorbed. All right, and then we have special names for these. So for example, a reaction where heat's given off, think fire. So fire gives off heat. A reaction where something absorbs heat, think cold pack, something that feels cold. Once again, it feels cold because it's absorbing the heat from your hand. So like if you put an ice pack on your hand, you know, you break the ice pack and all of a sudden it starts reacting, you put that on your hand, it feels cold to you because it's literally taking the heat from your hand and absorbing it into that reaction. And it makes it feel cold because you're losing heat. All right, so we have special names for both of these. The one where it gives off heat we call exothermic. Exo for like exiting, the heat is exiting the system or the reaction. And so we say it gives off the heat. And then an endothermic reaction would be something that absorbs heat, where heat goes into the reaction. All right, so the bottom one, if you ever try to dissolve sodium hydroxide pellets to make a sodium hydroxide solution, it's going to give off a good bit of heat. I actually did this one time and it had been a while since I made it and I wasn't thinking, and I literally almost melted a plastic bottle because it was giving off so much heat that it almost melted the bottle before I put it in a water bath to help deal with the heat. And then the bottom one, this is a common chemical that can be used in ice packs. I'm not saying it's not necessarily what is used, But ammonium nitrate is a good chemical to use to show this. You take ammonium nitrate, you put it in water, and dissolve it, all of a sudden it'll get cold. It'll start absorbing the heat from the surrounding area, making it feel cold. All right, so the scientific term for heat, and I don't know why they do this, is enthalpy. What's even crazier is the symbol for enthalpy is H. So we're not going to call it heat, we're going to call it enthalpy, but then we're still going to give it the symbol H. Confusing. Okay. I understand why they don't use an E, because E is for, well, energy and everything else. There are lots of E's out there, but so it's given the symbol H, and we can measure the enthalpy during a reaction and get charts that look like this depending upon what type of reaction you're looking at. So exothermic reactions, I say, go downhill because they're giving off enthalpy. You know that where it starts off here and where it ends, so it gives off heat. So it gives off this much heat. That's how much heat it gives off. Okay, so that's an exothermic reaction. It's going downhill. It's giving off energy. The way I like to think of it is think about a roller coaster. So on a roller coaster, you can put energy in to go up the hill. You got that chain that's pulling the roller coaster up the hill. You're putting energy into, endo meaning into. Okay, so endo means into, and we're going up the hill. Okay, so we're putting energy in to go up the hill. Like, or if you're somewhere where you go sledding in the winter, you got to walk up the hill. You got to put the energy in. And then an exothermic reaction, we're going down the hill, and the energy is being given off. Think of the roller coaster or the sled going down the hill. All that energy you put in to get up here is being given off as you go down in speed, right, in motion. So that's kind of how to think about these enthalpy diagrams. So once again, exothermic is leaving the system. Energy is leaving or exiting. And so you go downhill because that's energy leaving. Endo means energy is going into, and you're putting energy in, so therefore you go uphill on the diagram. As I stated before, the symbol for enthalpy is H. So we can also describe how H changes over the course of a reaction. We call this delta H. If you're not familiar, the big triangle there is the capital Greek letter delta. And it's so delta H, and anytime you see a delta, it's always final minus initial. So it's always H2 minus H1. So if you had delta T, it would be T2 minus T1. You can see it sometimes in algebra. They'll call it, that slope is delta Y over delta X. Y2 minus Y1 over X2 minus X1 would give you the slope. All right. So in an endothermic, H2 is here, H1 is here. And in an endothermic, it's the other way around. So in exothermic, delta H is going to be negative because I'm giving off heat, or I'm losing heat. Okay, once again, that should make intuitive sense that the heat is leaving, so it's being subtracted, so it's negative. In an endothermic reaction, the heat is being added or put into the system, so it's positive. So once again, so this part of heat and reactions to me makes logical sense. That exothermic, heat is leaving, it goes downhill, we call it negative delta H. Endothermic, the energy is going in, it's being put into the reaction, it goes uphill, and delta H is positive. All right, so looking at units, the SI unit for heat is the joule. Many reactions are measured in kilojoules because the joule is relatively small. So for example, if we look at some reactions, we can write them with the enthalpy inside of it, or we can write it with delta H written after. So here it is with the enthalpy being as part of the reaction, and then here is with it being written down here on the end. A lot of times when it's written in delta H form, it will be written as kilojoules per mole, usually meaning moles of the product being formed. And so that can get a little confusing as moles of what. But we can use this and stoichiometry in order to figure out the heat absorbed or released by any reaction. So let's look at an example. So if you dissolve 500 grams of sodium hydroxide, then how much heat will be given off? You're given this reaction. So just like we did with normal stoichiometry, we need to look at using the stoich road here. So we're starting with grams, and we need to go to moles because that's what we always have to do. So we're going to go grams of sodium hydroxide to moles of sodium hydroxide. And then we can go from moles, because of this reaction and the heat's in the reaction, I can do a stoichiometry relationship here. I can say 1 mole of this is equal to this many kilojoules. So that's what we do. And it ends up looking like this. So grams to moles, moles to kilojoules. So once again, that's what the stoic road looks like. And that's what the calculation looks like. So it works just like everything we've seen, nothing major. All right, when we were looking at the diagrams, you may have noticed something. You may have noticed these little humps. That we've got a hump here and a hump here. The hump is what we know as what's called the activation energy. All right, so it is energy that has to be added to the system above and beyond to make the reaction occur. So we'll kind of get an idea of what that looks like as we go along here. So the activation energy, which is E sub A, is the energy required to get the reaction to start, like I just said. And it's from the distance from the reactants to the top of the hump. So from here to here. That's your activation energy. It's not considered part of your delta H. Because delta H is from here to here. So it's kind of like extra energy that's required. So a match is a great example of this. So burning match is an exothermic process, but you have to strike the match first. And in striking the match, using that friction, you are adding energy to the match in order to get it to ignite. And then once it ignites, then the reaction is exothermic and goes downhill and gives off energy after that. But you have to add energy in first. Not all reactions have activation energy, but a lot of them do. And so that is something you will see. So that's kind of your brief intro to heat and reactions. And we'll look at how we do heat with calculations in the next lesson.